Wayne and the college, and certainly the Escambia Astronomers, good folks, and it's always a pleasure to drive 1,000 miles and come down here and give this talk. Seriously, I mean that. I am Clay Sherrod. I'm with the Arkansas Sky Observatories. It's a private observatory, and we do work in asteroids and near-Earth asteroids that are going to hit the Earth eventually, comets, and other interesting things. I tell people, they say, why do you do the studies that you do? I do those studies because I want to do something that doesn't bore me. And it's a lot of fun to be able to kind of do your own thing with your own observatory. So we are a private observatory. I do work with Harvard and NASA, and I'm working right now brand new information with a deal with Lockheed Martin on their very first private space venture into space to intercept an NEO and blow it up. So we are going to, hopefully next year we might have a presentation on our success or our lack of success. Throughout the presentation, we're going to have a few. This is going to be a little different. Now, last year, those of you that were here, and typically I try to make these fun for you, because listen, if you're going to sit through an hour of listening to me, you need some fun. Last year was Ancient Astronauts, and I think that was everyone's favorite. That's what everyone kept saying. I want to hear about aliens visiting the Earth. And it was. It was fun to put together. It was fun to present, and I hope it was fun for you to hear. Before that, we were talking about NEOs and comets crashing into the Earth, the evolution of the Earth. We talked about so many subjects. So tonight we're going to do something a little different, hopefully a little more fun, a little more educational. You're going to learn some history. You're going to learn a whole lot of astronomy. And you may learn a little bit about yourself. So occasionally, you'll see that I'm going to stop. We'll be talking. You'll be seeing, hopefully, some pretty pictures up here. A little bit of information you can take home with you. But I'll stop occasionally on one slide, and I may not say anything. It's not because I've lost my voice or gone deaf. I'll probably reach for my tea and take a sip while you take in the slide. I want you to look at it, think about it, and ponder it, because some of these are very, very deep philosophical slides. And I say that tongue-in-cheek because those of you that know me, I have a very dry wit. So anyway, enjoy the show. We have a remarkable ability when we study space to not only study the objects that are out there and enjoy their wonderment. I think most of you have telescopes or you've looked through them. And to see something with your own eye is the most remarkable phenomenon that the human can experience when you know how far away they are. And we're going to sort of take a lesson in that tonight. How big is space? How far away are these objects? How long has it taken their light to get to us? And what was Earth like when that light left that object and was traveling to Earth? So we're going to take us a short trip back in space, and while we do it, we have to go back in time as well. We've all heard about time machines, H.G. Wells' time machines. What a glorious thing. I think, particularly young boys, and I don't mean that, I guess that doesn't sound right. All of us when we're young, let me rephrase that, we kind of wonder about time travel. Wouldn't it be great to go back into the past and see what my grandmother was like when she was a young girl? Or go in the future and find out what the winning lottery numbers are going to be. We enjoy things like that, and that's just the human mind. We love to ponder things that we'll never achieve. So at one point, I decided I was going to come up with an idea of traveling in space. As a young kid, I invented time machines. I was sort of like the Rube Goldberg of my neighborhood. I would come up with these things that would never work, but in my mind, they were going to work eventually. And space and time. You're looking at the very first one, my Delorean. Obviously, Back to the Future, that kind of got us all thinking about what do we really need to do? Do we jazz up a machine and we can travel fast enough and go the speed of light, perhaps, or faster than the speed of light, and make a journey in time? And according to a lot of mathematicians and theorists, that is all really you've got to do. You've got to be able to manipulate time. And it goes back to one of the factors that I've talked to so many times with folks, that time is really a non-existent factor. Time doesn't even exist. Most of you that have been in astronomy long enough, you realize that time is for us. We have made up time as a convenient way for us to measure the passage of our bodies as we progress let's hope the ripe age of 95. Or that we see the progression of our family growing up. We see plants grow in the spring and die in the fall, or go into dormancy in the fall. That's time. It's a human thing. Time really does not exist. but in a spatial way. And according to the organization of the universe, we literally have to have time in order to make things work. So it's part of the mathematical equations. So in order for us to, instead of renting the rocket you just saw, and privatization of space, by the way, for those of you who are not aware of it, that's the way we're going. There's not going to be any NASA probably in several years in terms of actual sending things out there. It's going to be an organizational agency that's actually going to control what the government pays money for private enterprises to send into space. We're headed in that way very, very rapidly. This is not sudden, as it sounded like last couple of months. This has been going on now for 10 years. They've been trying to move toward the privatization of space travel. Totally different subject. We won't talk about it. So in other words, to get into space, and we want to be really cool about this, we have to have a cool vehicle. It has to look jazzy. It's got to look something like the USS Enterprise or even better than that. It's got to be sleek and, the ultra sports car. The Delorean just won't get it. And not only that, but this thing that we're traveling in, if we want to go time travel, which you're going to see is a real problem here in a minute. If you want to go time travel, you've got to have something, obviously, that's going to go 186,000 miles per second. It's impossible because theoretical physicists will tell you that if you go that fast, you begin to disassociate into a form of linearity where you are non-existent anymore. You turn into an energy form that literally is a linear form of atomic material. So what's the point? Why even travel? You're going to be a straight line when you get there. What are you going to do? You're not going to have feet. So we have to figure out a way to encase even our jalopy DeLorean or our rent-a-rocket. We're going to have to figure out a way to incorporate something that's going to be able to let us ride the speed of light without tearing ourselves up. Because if I'm going to make this trip, I don't care, there's no pay good enough for me to go in there as a straight line. I want to be me when I get there. So what do? Well, a lot of you have heard lately that they have discovered some subatomic particles that are similar to neutrinos that probably are going faster than the speed of light. Well, by the way, and of course they want to blow Einstein's theory of relativity completely out of the water because we've discovered these things. But, 2 weeks after they make this amazing discovery announcement, they're saying, we want someone else to redo the same experiment because we're not sure that we really did discover something faster than the speed of light. But for years and years, back when I first started, 4 years ago in astronomy, we had tachyons. We call these things tachyons. Tachyons are, and we don't use that word much anymore, but hey, this is my talk and we're going to talk about tachyons. Tachyons are particles that support the movement of light. And in order to do that, and this is kind of basic, in order to do that, they have to encircle a photon of light. The photon of light can move the speed of light, but it's also mass, it's matter, and we don't want that photon getting all delineated and be a point of a linear thing either. We want it to be a sunbeam, okay, and hit us in the face and give us suntans. It can't do that as a linearity. So the photon has to be intact. So for years and years, physicists have imagined that there is a subatomic particle that we used to call tachyons that encased the photons to protect them literally because they traveled faster than the speed of light, encircling like little bees around a honey nest or something, and they would protect that from the adverse effects of the speed of light. So in my way of thinking, my time machine, all we've got to do is encase anything in a tachyon bubble. We go out there and we wrestle, we find a bunch of tachyons flying around, we get our net, we take them and we put them around whatever we want to, in this case this spaceship, or my DeLorean, and we put them around that thing and it will be protected from the adverse effects of traveling at light speed because they travel faster. It's sort of like, but not quite analogous to a fly in your car. You're going down the interstate and you're going 70 miles an hour and this fly's been with you ever since you bought your burgers. And you can't get him out of the car, you've rolled the windows down, and here comes a car in front of you, you've got to get around this car. You speed up to 75. The fly's in the back seat, and all of a sudden he goes back and forth, and somehow or another he makes it to the front windshield of your car. Is that fly going 75 miles an hour? Well, technically, yes, with the inertia of the car that you're traveling in. Actually, it had to be going 75.1 or plus miles per hour. But in a tachyon bubble, in short, you can go maybe the speed of light, let's say. That's a good starting point. That's what we're going to use tonight. We would have to travel faster than the speed of light to really enjoy this journey. In our tachyon bubble, if we traveled at light speed, we all know 186,000 miles per second. I mean, that's tremendously fast. That's the equivalent of almost 12 million miles per minute. I mean, that'd be great, coming from Little Rock down here every year. In 1 light year, 6 trillion miles. I used to give a talk back in the 70s about the trillions. The distance to Alpha Centauri was 25 trillion miles. And I would tell everybody, we don't have any idea what that number means. We can't imagine 25 trillion. And now we have a national debt that's close to $25 trillion. So we can't understand it. We're an evolving intellectual society. So now we've figured out a way to understand trillions. But you know what? We really don't even need light speed. We don't need these machines. We don't need the tachyon bubbles. All we need is a telescope and someone to point it at the right place to be able to see our time machine in action. So let's go on our little journey. Now, what I want you to do all through this, every we'll call them stops, trip stops. We're going to go on a trip starting at Earth. We're going to go around the sun, head through the solar system, through the galaxy to the to the far expanse of our own galaxy, through the void of space to the next galaxy, and so forth until we get to the end of the universe. Very simple. Okay? And you're going to be seeing years popped up here. How many years passed? Let's say 165 years ago. Okay? That's going to be the time that the light you see from an object that I'm going to show you left that object. Okay? 165 years ago. That's how long it's taken going at light speed to get to your eyeballs. Most of the things that are on these screens you can see tonight with outside. You get in the dark sky, you'll be able to see most of these things. The interesting thing about it is that you're looking at it not as it is now, and Wayne teaches this in his classes. You're looking at things the way they were, in that case, 165 years ago. By the time the light finally penetrates your eyeball and into your brain for you to enjoy it, it's 165 years old. So you're literally looking back in the past. So at each one of these benchmark stops that we're going to take, try to be a step ahead of me before I show you the next slide and imagine what was going on Earth at that particular benchmark time when the light left from each of those objects. This is a good starting point. This is the audience participatory portion of my presentation, folks. Take a look at this, and seriously, I want you to participate here. What is the closest thing in this picture to you? If you were standing in this field, what's the closest thing to you? And tell me why you know that.
The ground.
Oh gosh, man, you're right. I think probably my footprint's in there somewhere. Your foot. Okay, the ground. Yeah. Okay. What's the next closest? The well. Okay, that's what I was looking for. Okay, the well is the closest thing in the picture, and the windmill. They're about the same distance. Okay, how do you know that? I mean, really, in your mind, how do we, as a thinking, logical creature, how do we know that that's closer to all that other stuff?
We don't know. It's larger.
It's larger. Okay. Okay. There's two factors. Number one, you're right. It is larger, so therefore it's probably closer. Okay. It's larger. Now that means larger to our eyes. It means larger as far as what we're actually seeing. But another phenomena is that mentally, thank goodness, you've looked in a book, even if you can't read, you've seen this picture. It's a windmill, and you know that windmills are pretty big things. So it's big and it's large, therefore it is the closest object. All right, what's besides ground? Let's not do ground again. Besides ground, what is the next closest thing in this picture?
The mountain.
The mountains, right. How do you know? Experience. They're smaller than the windmill.
Experience.
But they're larger than the horizon.
Yeah, you're farther away.
Okay, but how do you know? How do you know they're further away?
Depth perception.
Okay, all right, what are you talking about, though? What do you mean by depth perception? See, this is one of the neat things about the human mind. We can figure this stuff out. A raccoon can't do this, so you've got an edge right now. Stop and think about it for just a minute. Everybody said mountains, okay? We know what a mountain is, don't we? We know mountains are not molehills. We know they're big things. So big mountain, it's off at a distance relative to the windmill. We know they're bigger than the windmills, so that has to be the next closest thing because we know they're huge. Okay? Now look carefully at the picture. What's the next closest thing?
Moon.
The moon. There you go. Once again, how do you know? There's a couple of clues on this one. How do you know the moon's further away? It's behind the mountains. We've already established the mountains are closer, so it's behind the mountains. This is deductive reasoning. Now, typically, if you're an astronomy teacher and you take your beginning class out for the first time, this usually happens in high school, and a student will raise their hand and they'll say, all these stars that I'm seeing out here, are the brighter ones closer? And that's really a great question. You hope that you're going to have some student ask you that question. The answer is typically, overall, as a basic assumption, yes, if a star is brighter, it is going to be closer. Now, there are exceptions to that. Intrinsic brightness, which is actually the luminosity the star gives off, can fool you sometimes. Some brighter stars may be greater distances and appear fainter or appear closer because they're brighter, and yet they're actually further away. But for the most part, the brighter an object is in the sky, in the night sky, the closer it is to us. So the moon is very bright, it's very big. We, as human beings, understand what the moon is now, so we know that it also is the next furthest thing. Now, it becomes a little more complicated. Looking past the moon, what is the next closest object?
Like one of the
Nebulas.
Hard to say.
It is hard to say. Yes, it is. But what I just told you, based on the high school student that just asked me that question, brighter stars are typically closer than fainter stars. So what you're seeing is nebula is more than likely faint stars that we can't quite resolve way off in the distance in the Milky Way. So the brighter the stars that you see, the correct answer, for those of you that I know knew it, just embarrassed to raise your hand, the correct answer was the brighter stars. Those would be the next objects out. We might imagine that one of those bright stars would be a planet. I don't know that. So we'll just say the brighter stars are the next, and so forth. So that, in a nutshell, is kind of how you look at space. Typically, the brighter things, the things that appear larger to us, are indeed closer. We're going to start our journey by leaving the Earth, and we're going to travel to the Sun. We're going to travel at the speed of light. You see how long it takes to get to the Sun? Not very long. You're there in just literally a flash. We're going to slingshot past the Sun to the next planet, Mercury. Mercury is only 32 million. Wayne, how far is Mercury? 34 million miles from the Sun, something close to that. We'll just say in the 30s.
30 million.
And about 12 and a half minutes. This means we've gone from Earth, we've passed the Sun, visited the Sun, and said hi to all the solar people, and we've come back, and we're back to Mercury again. Only 12 minutes we've been gone. We've traveled a long way, speed of light. Boy, that's the answer to it, isn't it? You're going to see that's not at all the answer to space travel.
Mercury is on the other side of the sun, then.
Pardon?
From us. Evidently at 12 minutes.
Yeah, 12 minutes it would be on.
That would be the max. You're right. You're correct. That would be the maximum distance from the Sun and from the Earth. But now, just keep in mind for our journey, and this really, you're correct, but by the time we get out to the stars, it ain't going to matter, okay? So we're not going to be talking seconds and minutes. We're going to be talking, well, you'll see. And then we pass Venus. We're slingshotting back through the solar system. We're heading out to the realm, the very edge of the solar system. And so we're going to have to pass Mercury, only 15, nearly 16 minutes in our journey. And then we get back to the Earth. We've left Earth, we've gone around the Sun, we come back, we're back to Earth. 17 minutes we've been gone. You can fly by and, wave at your family as you go by. And look how long it takes just to get from the Earth to the Moon, our own Moon. We're not talking minutes. Just the total added time traveling light speed from the Earth to the Moon is only 1.3 seconds. Wow. Once you pass this realm, as this says, there's no going back. We're traveling now. We're picking up speed. We're aiming toward the end of the solar system and out into space. We pass Mars, which is the next distant planet out, and we've only spent 30 minutes getting there. For your information, for the spaceships that they're planning now that are going to be going to Mars, Russia is going to beat us to Mars, in case anybody's wondering. And the trip is supposed to take 9.3 months for the average trip to get to Mars. That's a long time for people in terms of manned space flight. That's as fast as we can go and feasibly be able to carry the payload that needs to be carried to the planet. And actually, most of the early spacecraft that visited Mars required about 9 months, about the same time it takes to have a baby. I don't know if there's a correlation there.
See us on Mars.
Now, once again, yeah, you have a chance to run for it. We forgot to lock the doors. Okay, we've only been talking about 30 minutes of space travel, and we're to the planet Mars. Now, from this point forward, the distances begin to increase incrementally. We're not even to Jupiter yet, okay? And notice at this point how much the distances and the times begin to increase dramatically. We go through the asteroid belt, and we're up to 38 minutes. That's about halfway from Mars to the planet Jupiter. Then we want to take from the asteroid belt onto the mighty planet Jupiter, and we're gone almost an hour, twice the length of time. Okay, we pass the mighty planet Jupiter, which does have enough gravity to perturb our spacecraft going out there at the speed of light because of its enormous gravity, and we begin to move on out into space. And obviously, like any trip, we have some problems along the way. Saturn we reach in an hour and a half. We've still not been gone very long. I mean, we can make it across, to Mobile in less time than this. What were you doing an hour and a half ago? Those of you that don't get this, we always meet at Golden Corral before these meetings, and an hour and a half ago, that's where we were. Now, that's what I'm talking about. This is really, if you really get your mind into it, this is fun, neat stuff. Because you look at Saturn, like go outside right now and see Saturn. I don't think it's out, but let's say you could. And you have to think what you're seeing is an hour and a half ago. It's not now. It's what you were doing an hour and a half ago is when the light left Saturn for you to see. Much further away is Uranus. You can see it's a total of almost 3 hours. 3 hours ago, you were probably getting ready to come over here. Then Neptune, even further out, over 4 hours. 4 hours ago, those of you that were unfortunate enough, you were probably getting ready to get off work and watching the time clock. And then Pluto, much further out. We're reaching the edge of what we call the planetary system, but not the solar system. Pluto is, it's a planet to me, but it is the furthest planet out that we have right now. Almost 6 hours. And 6 hours ago, we know what you were doing 6 hours ago. Now, this is kind of interesting because we're still in our solar system, just our neighborhood of planets. Okay? We haven't left the solar system, but we've traveled at the speed of light for 5 months now. Look how, did you catch that? We went from minutes and hours to 5 months, a half a year. And we have just now reached the inner edge of what we call the Oort comet cloud. The Oort comet cloud is kind of what it looks like in this picture. It's a large donut comprised of multitudes of particles left over from the original formation of the solar system, the sun and the planets. The comets come from here. All of them initially do, and then they get locked up and they appear to be coming from other places. But initially they all come from the big donut we call the Oort comet cloud. To reach this far into the solar system, this, by the way, is the orbit of Halley's Comet on the original orbit that it took way back when. But the inner edge of the Oort cloud is 5 months away, traveling at the speed of light. Now we begin to get into the real historical aspect. 5 months ago, May or June, you were getting out of school. Some of you were getting ready to take tests, getting ready for vacation. Osama bin Laden had been assassinated, dumped in the ocean. And so many things were different back then. Yankee Stadium got torn down. That was a dear one to me. So a lot has happened in 6 months. But as the light from the Oort cloud, just the distance into our inner solar system, it took 5 months just to get here. And all this was going on when that light left. And then the outer edge, which is the other side of the donut, it's over 1 year. 1 year of travel time at the speed of light to get there. We're on the very outer edges, the fringes of our solar system, where the sun has no more gravitational influence. 1 year. What was happening 1 year ago today? Well, some of you were listening to me, sitting right here. And if you remember, the Chilean miners were all trapped, and as we were staying at the hotel out on the beach, they were pulling them up one by one through a big tube. So it's interesting to look at that 1 year ago today. But now, as we leave the solar system, which has been very, very close, the next step is to go into the stars. Every star that you see out there tonight, any night you look up, every single star you see is in our Milky Way galaxy. There are no exceptions to that. Every single star belongs to our Milky Way. Now, we get beyond the Milky Way, and we can begin to see other stars in other Milky Way galaxies. And you'll see that here in just a minute. But we're going to enter the realm of stars now, which the time and the history become incrementally higher. Instead of talking now about hours and minutes and days and months, we're really talking about history. Because every object you're about to see has history behind it. The light that falls on those cameras that takes these pictures was on its way for years, decades, centuries, millennia. So pay attention closely.
Oh, God.
Our closest star is Alpha Proxima Centauri. It's a little triple star system only 4.5 light years away. Sounds like a piece of cake. 4.5 years to get there, 4.5 years to get back at the speed of light. That is the closest star to us. So if we're traveling the shortest distance, if you use your Google Maps, it'll show you that if you're going out to the end of the universe, go by Alpha Centauri. It's the shortest route. And 4.5 years ago, we had things happening on Earth. When Alpha Centauri's light began its journey here, the little girl in England was abducted, or from England was abducted in Portugal, and that made the headlines while her parents were eating in a fancy restaurant, 2 blocks away. And they discovered the tomb of Herod the Great 4.5 years ago. The bright star Sirius, it's up overhead about 2 o'clock tonight, at 2 o'clock in the morning. And the brilliant star. And this is one that really gets me. The bright stars are my favorite. You go out and you look at those stars and you see that brilliance, in binoculars, small telescope view from the naked eye. And you really realize for the first time, I'm not really seeing that star as it is right now. I'm seeing it as it was 10 years ago. When that light was burst out of Sirius 10 years ago, what was happening on planet Earth? Remember, I asked you to try to be ahead of me on this. 10 years ago. 9/11. That's right. So that light has been on its journey for 10 years while we've suffered through all of this, and we finally get to see it tonight. Isn't that interesting? They're almost like historical markers to me. They're benchmarks. And one of the things that I ask everyone to do, particularly if you're into astronomy or you know someone who would help you do this, if you lose a loved one, or if you have a new birth in your family on a certain date and a certain year, go to someone in astronomy and ask them what star began its light journey to Earth on those particular dates. And mark it down, write it down, put it in their baby book, put it in there with the packet that they give you from the funeral home with the obituary. It's a very, very important thing to do because it's a milestone, and there's nothing more significant milestone than something like the star Sirius or some of these objects that you're about to see. Even further away, 25 light years away, the light you see that this camera took was 25 years old when it fell into the camera. 25 years ago, the internet was absolutely in its infancy. Computers had been around a little while, and they were becoming more and more sophisticated, but for the most part, the internet was still just kind of a toy. We couldn't do without it now, could we? It's amazing what 25 years makes. And maybe even more memorable, look what happened 25 years ago. You know, it's almost catastrophic when you think of it that way. You look at that beautiful bright blue star Vega, and we show everybody Vega at star parties. You know, here's this brilliant star. Next time you have a star party and you show them Vega, particularly this year, ask them, do you know what happened 25 years ago when that light you're seeing left that star? I remember pulling over on Interstate 40. I was so devastated about the news from the Challenger explosion. You know, it impacted every one of us. And then those of it on the bright side, Halley's Comet was coming back, you know. We were all excited about a comet no-show, essentially. And so things happen. And a little history was made. Another benchmark is Capella, 41 light years away. What was going on when the light left that star? 41 years ago, when the light left that star, what was going on? Got to do some quick math here. Boy, things were different. Look at there. Disco was, it ruled.
Oh, God.
Disco. And look at all this stuff. Now, what amazes me the most is look in the lower left here. They were just now getting worried about global warming. You know, the UN chief. The UN could care less about global warming now. But the UN chief says he's worried about global warming. And boy, was he ever right. You know? And look, I love the middle picture. Here's Elvis in a suit and tie and Richard Nixon with his big wide lapel collar deal, collar open and all the hair hanging out on his chest. I mean, is that not? And of course, Cassius Clay, Muhammad Ali. But there are more important things that did happen 41 years ago. Doonesbury got started in the comic strips. The very first strip, 1970. And Arkansas Sky Observatory was established 41 years ago today. Aldebaran, the bright star in Taurus. Now, Aldebaran is the bright star. This is actually a cluster of stars called the Hyades. It's much further away. Aldebaran's not part of the Hyades. But Aldebaran is 65 light years away. The light leaving that star has a historical significance too. And you're going to find out that every time we see a star in a benchmark, there's a war going on. Every single time. World War II we were right in the midst of World War II. The electronic computer was unveiled for the first time. It took up an entire building, one computer. Of course, it couldn't process anything faster than the Commodore 64 when it finally came out. But the very first world's computer in 1946.